Hello audience, today I'm going to give a tutorial on an exciting emerging area called learning to optimize, and I'm going to focus on one methodology of learning to optimize, which is called algorithm unfolding or algorithm unrolling, same meaning. I'm Wo Taoyin from Decision Intelligence Lab of Damo Academy, a research center of Alibaba Group US. So before I start, I want to say that lots of the materials of this tutorial is taken from these two papers, the A-Lista paper published in ICLR'19 and Hyperlista published in last year's New Rips. And these are my co-authors from UT Austin and from Alibaba US. And also there are materials taken from these two survey papers. And one of our survey papers, Learning to Optimize, a primer and a benchmark, have been accepted to appear in the Journal of Machine Learning Research. And I also looked at the early survey, Algorithm Unrolling, Interpretable, Efficient Deep Learning for Signal and Image Processing, which covers more applications than this particular tutorial. And it was written in 2019 and published in last year's IEEE Signal Processing magazine. I encourage all the interested audience to download the code and try to reproduce the results. And several slides of the tutorial were created with the help from my colleague Jialing Liu at Alibaba and Xiaohan Chen, who's graduating from UT Austin, Professor Zhang Yang Wang's group. So before we talk about learning to optimize, I want to compare machine learning with optimization. Machine learning is induction. Usually, you are given a set of problems and answers as pairs, as training data, so that the machine learning model can be trained to give answers to the problems you see in the future. However, optimization is prescription. In optimization, there's actually no training data. And when it comes to making decision or solving a problem, you're given the problems and specifically the set of evaluations which specify what are feasible solutions and what are the qualities of a solution in terms of certain function values. And optimization find answers to the problems that with nearly optimal or optimal evaluations. So these are very two different paradigms. And learning to optimize tries to combine these two paradigms to obtain better solutions in shorter time by learning from the records of optimization in the past. So before I start talking about learning to optimize, it's interesting to compare learned optimizer or learned optimization algorithms to classic optimization algorithms. Classic optimization algorithms are those built by experts based on their theoretical understanding and experience. Examples are the simplex method by George Danzig and Nesterov's accelerated gradient descent method. These algorithms can be written usually in several lines. In the case of Nesterov, you can write it down in 2 lines. And when it comes to applying them, the practitioners will have a problem at hand and they usually reformulate the problem into the form that one of these classic optimization algorithms can solve, and then they pick the algorithm. They may have 1 or 2 parameters to tune, but that's it in terms of tuning. Learning to optimize has practitioners more involved in the design process of the algorithm. The experts only propose learning to optimize templates and the procedure of training the templates. It is the practitioner's task to pick an appropriate template, preparing all the training data, apply the training procedure to obtain a trained algorithm, and then they expect to use this trained algorithm to future problems that are similar to the training problems. Learning to optimize is based on the observation that many optimization algorithms are similar in form to neural networks. Consider this neural network where xk is the output of the previous layer, and and some matrix or linear operator applied to the input from the previous layer plus offset, and then goes through some nonlinear operator. And this is a typical layer of neural network. And consider, in comparison, a iteration for constraint least squares, where we want to minimize the 2 norm squared of ax minus b, subject to x belongs to the constraint set C. The inner step is gradient descent to the objective, and the projection step project the output to the constraint set. This is a linear operator with offset, and projection to C is usually a nonlinear operator. However, the difference is in neural networks, typically all the nonlinear, linear, and offset at every layer depend on the layer you choose, and they can be trained together. However, in optimization, they're fixed. They come from the problem definition, and you may have a step size parameter to tune, but that's pretty much it. So a natural idea is to relax the traditional optimization into a neural network, and then use deep learning technologies to train the neural network and obtain an improved optimization algorithm. There are actually 2 ways to do this. One way is to start from a neural network and train for optimization. The other approach is to start from a classic optimization method and relax certain things to train. Specifically, the first method is called the model-free method. It's basically start with full freedom and have the parameter trained in fully data-driven way. And the trained neural network will take the input of an optimization problem and output an approximate solution to the optimization problem. The benefit of this approach is at inference, it's very fast because there are fewer layers. Usually there are fewer layers than classic optimization algorithms. However, because there might be too many parameters to train, the training can be slow, can be tricky, and there's usually no guarantee of the solution quality. You may get poor generalization, and overall, this method is not very popular or not very general. A more popular methodology is called model-based learning to optimize. It starts from some kind of existing optimization algorithm and modify them to make part of them deep learning-like. There are different approaches: algorithm unrolling, plug and play, deep equilibrium, or fixed point network. And as I mentioned, you can find these the different approaches in the survey paper we have. And this tutorial will focus on the first part, algorithms unfolding. The remaining of this tutorial will be divided into these parts. We will define algorithm unrolling and give a couple of examples. And we will switch to focus on this lista series work, which is simple enough to explain in the tutorial. And over the last 10 years, we see a 2 order of magnitude speed up and also improvement of generalization performance. We'll briefly mention some of the series and then conclude this tutorial. Algorithm unfolding or algorithm unrolling consists of 2 steps. You pick a classic iteration, unroll it to make it look like a neural network, and then most importantly is the second step. You choose certain parameters to free and train them like you train a neural network. To be concrete, let's look at this lasso example. So lasso is an optimization model where the goal is to recover a sparse vector, x true, from its linear measurements, which may be corrupted by noise. So in other words, you have B, you have A, try to recover a sparse solution. One of the most common models of doing this is the lasso model, which minimizes the least squares objective plus a penalty parameter lambda times the L1. And this model, I choose this model because not only it is simple enough, it has lots of fascinating results, it is also the basis of more complicated models that deal with matrices and problem subspaces or feature selections in more application area. The One of the most basic and simplest iteration for lasso model is the iterative soft thresholding algorithm, or ISTA. The inner iteration is a gradient descent to the least squares term with a step size alpha, and the outer iteration is a proximal mapping corresponding to L1 norm. And this is also called the soft thresholding nonlinear operator. And the threshold depends on lambda and alpha, with a properly small step size alpha, or you can use line search to determine alpha for each iteration, and this iteration will converge to a solution to this problem. Roughly speaking, the inner step reduces the least squares and outer step reduces L1. We can introduce scalar theta for the threshold and matrices W1 and W2 that depend on the sensing matrix A in lasso model. And this would allow us to rewrite ISTA equivalently in this form. So this is exactly the same iteration as before, but now it looks like a neural network. There's a linear operator, there's an offset, and there's a nonlinear operator. The idea by Gregor and Jan Kuhn back about 12 years ago is to free these variables and let them depend on the iteration. So they're going to be a sequence of theta, sequence of potentially different thresholds, and sequence of potentially different W1k and W2k, which will be free parameters to define this iteration. And this looks like a neural network, and this is a neural network scheme, flow scheme. Once these parameters are chosen, the algorithm or the network is defined. You can apply it to approximately solve a lasso problem or recover this sparse signal. And then they determine, in order to determine the sequence of parameters, they created a synthetic data. The synthetic data are going to use the same A, but lots of different X, and for every X, there are going to be independent noise. So in other words, they fix a random matrix A, generate a set of sparse signals Xi true with different supports. In other words, the location of non-zeros and those values are different. And then they take noisy linear measurements of those sparse signals and call these true signals and linear measurements as training data. And then they write down this training problem where for every sample point, which is a pair of true data and its corresponding linear measurements, you compare the output of the case layer ISTA network to the true signal, and you decide the parameters in the network such that the case layer output is as close to the true signal as possible over the entire training data set. And they found amazing results. First of all, they only fixed k to 16. In other words, there are only 16 iterations of their method, or 16 layers of their neural network. And in this graph, the horizontal axis is the number of iterations or number of layers. Vertical axis is the normalized mean square error in dB. In other words, it's in the log scale. And these red curves corresponding to the ISTA progress corresponding to different lambda, different choice of penalty parameter. And this blue is the progress of their learned algorithm tested on a set of data, particular set of data. And you can see that the error, first of all, it decreases really fast, about 50 times faster than this traditional ISTA algorithm. And the end results is also better. So in other words, the trained network, because it's trained to recover the true signal rather than trained to solve the lasso problem, when you compare the results of the true signal, it is actually better than the solution of the lasso problem corresponding to a different lambda. So this idea was very quickly picked up by people in this community, actually in different communities. They have applied similar ideas to Unroll ADMM, to Unroll PDHG. ADMM stands for Alternating Direction Method of Multipliers. PDHD stands for Primal Dual Hybrid Gradient Algorithm, and these are operator splitting algorithms that are capable of solving fairly complicated optimization problems, especially involving non-smooth terms. And researchers have applied the ideas to different sets of problems. For example, image denoising, deblurring, super resolution, segmentation, medical imaging, remote sensing, and wireless communication and other signal processing techniques. Here I'm going to show you two sets of examples. The first application is CT reconstruction. Imagine that X stands for an image, for example, an image of a slice of your body, and A stands for the Rodon transform, which basically takes several line integrals. And the goal is to, from the results of the line integrals, to recover the true signal, the true image. We want to, if we are able to recover better signals, we are able to potentially not only reduce the image reconstruction time and improve its quality, but we also may be able to reduce the number of line integrals. In other words, the radiation dosage that's delivered to the patient. So this is a very important application. So classic total variation was down to CT imaging around 2008. So this is about a 14-year-old technology. And on this particular test I'm showing you, TV did not do a good job. And 5 years ago, CNN did much better job, and this unrolled algorithm give you cleaner image. Here's another application called image deblurring, where X stands for the image. This stands for convolution, which simulates the process of causing an image, one way to cause the image to blur, and the measurement may be corrupted by noise. And in this work, the idea is to use information from the image and from our knowledge about the image to create a sharper image than the input image. Total variation is a traditional technique, classic model, classic algorithm to do this problem. And in this example, it did not recover correctly the blurring kernel and also caused the image to distort. And this is the result of CNN, and this is the result of unrolling, which not only recovers highly correct blurring kernel, but also give you much sharper, less distorted image. Okay, so back to the method of algorithm unrolling itself. If you download the original code or download these applications software code and practice them, you realize there are several challenges. One, there might be too many parameters to train, especially in imaging examples. Second, it's actually difficult to choose K. If you choose K small, you may not be able to iterate enough to get a high quality solution. If you choose K large, training becomes difficult because deeper the layer, the more difficult the backpropagation will be. Also, when you apply such a technique to critical decision-making processes like medical imaging and operations research, the practitioners usually require the method to be interpretable. They need to understand why the method makes such a decision or generates such results, and they want be able to improve the method gradually as they collect more data. So they tend to require the method to more like a white box, explainable, and explainability is often associated with this notion of generalization and reliability. Also, when you apply a learned algorithm to out of distribution data, you would naturally require certain kind of safeguard such that the performance will be at least comparable to classic algorithms. And these are the challenges of algorithm unrolling. And fortunately, over the years, they have been more or less addressed for the lasso model for the sparse coding problem. So the first idea we had about 5 years ago is to theoretically study how these what these parameters should satisfy and numerically verify that. Assume no noise, and if we require the sequence to converge to the true signal and then playing with gradient and optimality condition, we realize that W2k plus W1k times matrix A must converge to identity as k goes to infinity. And also the softest thresholding threshold must converge to 0 as k goes to infinity. And we went back to our training and look at the W we generated, look at theta we generated. In fact, as k increases, they are approaching the limit. So we cannot really do much at this moment to on theta k. We cannot, for example, fix theta k to 0 or to a small number, because that'll eliminate the ability of selecting out the most important features or most important components in X. However, we tried to just let this matrix equal to identity for all k instead of waiting it to converge. That is, we learn W1k and then set W2k according to this formula, which is motivated by the limit on the last slide. This yields this new iteration where W1 and theta k, W1k and theta k are the parameters to learn. We have eliminated W2k by this equation. We call it weight coupling. By clear, simple observation, we have reduced the parameters from n squared k plus mn k, where this part corresponding to W2, this part corresponding to W1, to this number. And this is quite a significant reduction because often n, which is the number of the dimension of the signal, is more than m, which is the number of measurements. So after this reduction, we also observe training appears to be more stable. In other words, it's easier and quicker to train. And then we incorporate another technique, which we I did at Rice University with my co-authors Elaine Hale, Ying Zhang, and Yilun Wang, about more than 10 years ago. The idea is that each iteration, we let the largest few components in xk to bypass softest thresholding. The reasoning behind this is when the bypass non-zeros are true non-zeros in the signal, then softest threshold then you will avoid the bias induced by softest thresholding on those components. Therefore, if you bypass the correct or mostly correct set of non-zeros, you reduce bias, which help you converge faster and also help you get better signal. So in this neural network, we also incorporate this technique. So instead of this eta operator, it's no longer just the pure softest thresholding. There's the first few largest components that are bypassed. They're just like identity on those components. So how many components to bypass? Well, this depends on the data. Therefore, we also let it be a training parameter or trainable parameter. So here we're going to do a numerical experiment of original Lista and Lista incorporating these new ideas with coupling, which eliminates W2k, support selection, as well as with coupling together with support selection. And we test on NMSE in dB, and the test I show here are using synthetic data, but you can also do it on real data like images. In the synthetic data, sparsity is about 50, and the signal dimension is 500, and we're taking half of the measurements of the dimension. The sensing matrix have IID components, and the magnitudes of the non-zeros in the sparse signal are sampled from standard Gaussian. And we also add noise to the measurements in some tests, and when noise is added, it's measured by signal to noise ratio. And this is the comparison or recovery performance over the number of iterations or number of layers of several algorithms. These two red algorithms are ESTA and FISTA algorithm. FISTA is a network of accelerated ISTA algorithm, and they usually take a few hundreds of iterations to converge. So 16 iterations, you won't see much of a progress. So more progress are seen on these learned methods. The red one is approximate message passing. The green one is the Greg and LeCun's Lista algorithm, which learns everything. And Lista CP is the weight coupling, which learns only W1 and set W2 according to W1. As you can see that the coupling technique improve the convergence speed and have the same final quality. Now let's add support selection, and this is the noises test. Therefore, the signal to noise ratio of the noise is of the measurement is infinity. Therefore, we are able to reach the lower dB. Normalize the mean square error. At the bottom is Lista coupling with support selection, and this is Lista with support selection. This is Lista and Lista couple. There are a few others like learned AMP, approximate message passing, which is better than approximate message passing. The relative positions of these methods are still remain the same when we add noise to the measurements. So again, the best one is Lista coupling with support selection. So after that work, we sit there and ask ourselves, are there other properties, theoretical analysis properties, analytic properties that we can use to further simplify the deep learning process? And inspired by our analysis and also by observations, we start to think, well, during the analysis, we figure out, we tried to do like some lower bound analysis, upper bound performance and guarantee analysis. We realized there's no reason to make W vary at different iterations. It seems the same W, one W should work. Therefore, we tried to tie all the WK together. So we just call it W. So instead of a W1K depend on K, now there's like one W. And you're going to learn that one W, but you're going to need to learn the step size and thresholding parameters, which still depend on the iteration. Well, this has a huge reduction in number of parameters to learn from M times N times the number of layers of neural network to Mn, which is the size of W, plus K, which is the size of these scalar series. And we did it. We go to training and then observe the test results. The test results is amazing. The curve almost matches Lista couple with support selection, support selection, and the final results are even a little better, with a couple of dBs improvement. So it seems indeed W doesn't have to vary from iteration to iteration. So with that experience, we went further in another work, and we start to think, well, if there's only a W to learn, and this W performs certain role, is it possible to figure out in better ways of a W rather than learning? Maybe using an analytic formula to come up with a W. Well, we resort to this concept called coherence. Some people call it mutual coherence. So coherence of a matrix with normalized column is the maximum inner product, the absolute value of the inner products of different columns, which is the maximum cross correlation between pairs of columns. We will have a low coherence sparse recovery from the measurement using A will be easier. And this is done by Donahoe and Elad back in 2003. And there's also mutual coherence between two different matrices. Suppose matrix A has normalized columns, and then the mutual coherence between two different matrices are their cross products, the maximum of their cross inner products. Numerically, we plotted the mutual coherence of W to A, and we plotted against the training epochs. Here is one particular example. You fix some kind of random A, and then you let pi lista to get trained, and during the process you plot the mutual coherence of the trained W to A. As training progresses, the mutual coherence gets smaller and smaller, and which of course motivate us to pursue the best mutual coherence, pursue a W with the best mutual coherence. And that is called A-lista, where A stands for analytic lista, which is a new paper that we published in ICAR, which actually receives like one of the best review evaluations at ICAR. So A-lista stands for analytic lista, which basically determines W without training. So this is the formulation we do for W. Instead of using the standard definition of mutual coherence, we just use Frobenius norm, which gives us an easier convex quadratic problem. And so actually the solution can be written in a closed form, which involves certain inversion of the A transpose A matrix, A transpose matrix, and pick a solution. And with that W fixed, there remains two sequences of scalars to learn. One is the step size, the other is the thresholding thresholds. And this again significantly reduces the number of parameters. You basically get rid of W, so you only have about 32 parameters to train when the network has 16 layers. The training only takes minutes. And then we test it. Amazingly, the results are just as good. This is the noise, lossless case, no sampling noise. This is with sampling noise. Horizontal axis is number of layers, and vertical axis is the accuracy in log scale. And A-lista is the black. Well, A-lista is not the best. However, it's the most easiest to train. It takes only minutes to train, has very few parameters, and actually more stable to train too. And so over these set of works, we have gradually reduced the number of parameters, which corresponding to the reduction in training times from hours to just minutes. Performance-wise, Lista is actually is similar to Lista CPSS, and which was beaten by pi-lista and A-lista. So we move on to think about robustness of A-lista. So before, for every matrix A, we have to train a W. Would it be possible to speed up, the generation of W? So consider this system where the sampling matrix is no longer a fixed matrix A, but perturbation of this fixed matrix A. So given the perturbed sampling matrix and the measurements, recover X. So in other words, now the neural network generated algorithm must be able to handle different A tilde. So recall we solve a quadratic program in order to map A to W. Well, this itself can be unrolled and made into a neural network with trainable parameters. So without going into details, I'll just give you the overall idea. So we train a neural network, which we call the encoder, with many pairs of noise corrupted A matrix, which is called A tilde, and the corresponding solution W tilde of the quadratic program. And then with that tilde and this A tilde, we generate a bunch of signals and their measurements, and we train A-lista, which we call the decoder. And then we combine the encoder and decoder into one bigger process and jointly train both of them with many pairs of these A, Y, W, and X. And the end result will be given A tilde and Y tilde. the whole network will directly produce X. And without, for asking the user to call a solver on the quadratic program to get W first. So to illustrate this robustness, we fix an A, and we first train a non-robust lista with their W matrix obtained with the clean A, and then we also train robust lista with the perturbed A, which is are those A tildes with this amount of Gaussian noise in the entries of A, and then we test both this non-robust lista methods, including A lista and the robust A lista, on problems with perturbed A, and we vary the amount of perturbations in the entries of A from 0 all the way to 0.03, and actually go a little higher, and you can see the recover results. Because this robust A lista is trained with the measurement noise, with the noise of A in mind, it does better. And this is a very recent result called A-lista, and it has a few ideas in this paper, and I think one of the most important idea is a small but important modification to A-lista. And this is A-lista. Recall we generate AW and then train step size and thresholds. Instead of training W, they say let's train A transpose U instead. When we're gonna make U positive, symmetric positive definite, and train U. Now, this important change make this, in particular, this term to correspond to a descent direction, and for the whole iteration to correspond to a certain Neapel function, which can govern the convergence of this algorithm. And also, because there is a Neapel function, you can now train without bothering first generating the true signal. You can just train with the existing measurement data without knowing the true signal. In addition, this paper also considered momentum, Poyak momentum added to their iteration. There's going to be some kind of extra term which depends on xk minus xk minus 1 with some parameter in front. So let me stop this progress for now and talk about the theory. So what can we say about this list approach? So this A-lista paper has several theorems. So the first theorem basically says, given low mutual coherence between these two matrices, and any sparse signal with significant components, in other words, the non-zeros have to be above certain threshold, and then there exist network parameters in the A-lista form such that the iteration will converge linearly for those signals with high probability. So this is a positive result. Basically it says you certainly can possibly train A-lista to get linear convergence. So A-lista improved these results to get similar linear convergence, but robust also to the dictionary perturbations or the perturbations in matrix A. Step lista provides necessary conditions that model converge to the lasso solution. So recall, lots of these works were pursuing the true signal, the true sparse signal, but sometimes you do want to just get the lasso solution. So they provide necessary conditions. There have been a sequence of papers that analyze the Rademacher complexity of lista and its variants. Finally, there's a negative result from our paper 2 years ago. We show even if you do lista, in other words, train any W1K, W2K, theta K, no matter what sequence of these parameters you train, if you consider a set of sparse vectors X with uniform random supports and values, and then linear convergence is the best you can get with high probability, in other words, for most of such sparse signals. You're not able to get, in particular, superlinear convergence because you use one set of trained network parameters for fixed A matrix, but varying sparse varying sparse signals. And once you do it for all sparse signals, you can't do better than linear convergence. And this is what the theorem says. So Hyperlista actually says, well, we can do better than linear convergence by making further changes. Here are two changes. First, you have to replace soft thresholding with support selection kind of soft thresholding. We call it hybrid thresholding. The p largest entries, pk largest entries of xk will be bypassed. And then, well, this seemingly adds another sequence of parameters pk to train. But this paper come up with analytic formulas which were motivated by their analysis for the parameters, for the step size parameter, for the momentum extrapolation, for pk and theta k. And these formulas still have three hyperparameters, which are three scalars to train. Well, you can train them based on data, but you don't need to use SGD. You can just use grid search to get the global optimum. If there are just a few enough parameters. The significance is, which is a little behind the hood. Now, these formulas are going to be adapt to the signal, adapt to xk, as you will see. Therefore, you can call them nearly instance optimal. And by going instance optimal rather than just the one set of signals for all sparse signals, one set of parameters for all sparse signals, you can do better than superlinear. You do better than linear convergence. You get superlinear convergence. So I say superlinear-like because this is finite layer, and in the basically in the first several layers, the error gonna decrease not like a line in log scale, but decrease better than a straight line in the log scale part. So you get superlinear-like convergence. There's a theorem about it, and there's also numerical results about it. So I'll just show you what these formulas look like. This is how we select the soft threshold. It depends on an unknown parameter C1. Mu is mutual coherence and L1 norm of A pseudo inverse times A xk minus B. Well, xk is something you know. It's the output of the previous layer. And beta k depends on this, and pk has a little more complicated formula. The step size is chosen and fixed as 1 in this paper. So we have reduced parameters from k, from like 32 to just a 3. We can do a grid search. And the results are even better than before, amazingly. In noiseless, then training data and test data are come from the same distribution. Hyperlista does now even better than A-lista and some improvements of A-lista. And then we start to test on out of distribution, different kinds of out of distribution problems, which start to fail other methods, but this Hyperlista stays robust. We change sparsity from 10% to 15%. So a Hyperlista still works really well. We change the variance of the non-zero elements of the true signal to 2, and other methods start to perform pretty poorly. And Hyperlista, the same network with those formulas, still works. And we also change the noise level. And in this case, many methods still work, but Hyperlista works the best. So time is up, and I want to briefly mention these uncovered list of topics. This paper, Moreau and Bruna have proposed to understand Lista by the similarity by building a link between Lista and the matrix factorization method. It's very interesting. And this paper proposed learned iterative hard thresholding coupled iteration, which also motivated one of our papers. This paper have proposed a gated mechanism to improve Lista. And this paper have proposed a minimal mean square error estimator-based shrinkage function in Lista, improving the performance of Lista. And this paper proposed to use non-convex function-induced regularizers in Lista, so you don't have to restrict yourself to L1 or other convex regularizer. You can use non-convex regularizers. One of our papers by my students and Howard Heaton and others introduced a safeguard wrapper for Lista and similar methods for ADM, for learned ADMM, learned primal dual, and other learned operator splitting algorithms. And this safeguard wrapper will ensure that when you apply this network to unseen problem, or out of distribution problems, you get at least the same performance as traditional algorithm. And also very interesting line of work, consider K is very large or K is infinity. In this case, Lista becomes very difficult to train. And you have to do some complicated curriculum training, and you may still not get stable training. So instead, we just look at the fixed point formula or the equilibrium. And there's a serious paper by Coulter's group, and we also have a serious paper in my group and others in Rebecca Vadis' group studied created this idea and applied it to monotone fixed point networks, non-expensive fixed point networks and monotone operators, and demonstrated that such technique, when allowing K to infinity, has better image recovery quality than algorithm unfolding. To wrap up, let me summarize this talk. So hopefully I have demonstrated there's a huge room for optimization to improve in terms of speed and quality, solution quality. And one of the viable methods is to incorporate training and machine learning ideas into optimization. So this training, this integration, integrates data-driven methods, which tends to be slow at training, fast at inference, and adaptive to the data at hand, data-driven training, with the analytic method, which is faster, very fast, well, of course, no training, and slow at may take many iterations, when you solve a problem, and work quite universally to at least the set of problems that the theory has indicated. Combine them, you can get faster train, faster inference, and methods that have better performance for the data at your hand. However, despite the success in sparse coding, much less success can be set on other algorithms unfolding, either unfolding other algorithms or for different models. So I think this success of observation and distilling formulas, analytic formulas, therefore improve generalization performance in HyperLista can certainly be done in many other algorithms. So thank you very much. And finally, let me just say there are the set of slides which will be posted online also include all the references. When you click on if you click on the PDF that we post on our CVPR tutorial website, in the slides you will be able to jump into the specific reference, the page that's showing the reference. Thank you very much for listening.